Well, thanks everyone for coming. My name is Jorge. I do a bunch of different things at Sysdig. How many people know Sysdig here? Please raise your hands. Oh, so quite a few. For the ones who know Sysdig, we have a few different projects. This is my screensaver. We have a few different projects. The most important one is an open source troubleshooting tool that works very well with containers and Kubernetes. We have a monitoring tool for the Docker and Kubernetes and other orchestration systems. But today, I'm not going to talk about any of those. I'm going to talk about a kind of experimental project, a pet project, actually. We released it a few months ago. It's fully open source. You can just go to GitHub and see how does it look, how does it work. It's based on our system call tracing technology. And I'm going to use some slides to show you basically how it works. And then I'll try to focus mostly on demo. So please, if something fails, excuse me, because this is really dangerous. So our tracing or system call tracing tool, it's different from open tracing or other different tracing tools. It's like more useful probably for sysadmins. And when like building our container troubleshooting tool, Sysdig, we saw that previously sysadmins, they were using all these kind of tools for doing troubleshooting. And when we released Sysdig, we saw that they really liked the tool because basically they could ditch all these tools that they were not working with namespaces, with containers, and they could start using Sysdig. But then with containers, like how can you look at what's the code doing? Like we have all these changes with containers, namespaces, so on. So there are quite a bunch of different tracing tools. All the open tracing, paste, Simpkin, Dapper, there are a bunch of them. There are other commercial tracing tools that are quite nice. And then there is people who they don't want to use neither of both, and they do some in-house hacks. So they start using StatC to report metrics on the performance on their code. They do just print. They do some logging, although might have not all the information. So we thought, what if we have something open source, everyone can use it, that it's really simple. We don't want to do funky stuff. It's like uptime, like the basic troubleshooting tools we showed before. And something that is very easy to use, no like eBPF-based tools like BCCC. Something lightweight that didn't have a huge performance impact. And that could work everywhere pretty much, like Sysdig. Containers, no containers, everywhere. So we thought, we have the technology. We have Sysdig open source that it does native container troubleshooting. We also have the monitoring tool. I'm not going to talk about that. What if we use the technology to do some kind of system called tracing? For the ones who know Sysdig, you can ignore me over the next couple of minutes, but I'm going to explain basically how Sysdig technology works for the ones that you don't know. Basically, what we do is instead of instrumenting code or services, we look at the kernel level. So we have apps running directly on the host. We might have containers. Basically, what we do, we load the kernel module. This kernel module intercepts or captures all the system calls. We put them in a shared ring memory buffer, and then we send it to the user space where we do all kind of formatting, reporting, some kind of magic. We can dump into a file. So it's like pretty much like TCP dump, but for system calls. So we can capture all the system calls that actually we transform them to events because we keep like some relationship between them. We can apply filters. We can run scripts. I'll show you some examples of these scripts. So we call them chisels. You can dump into a file. You can run analysis afterward. Because we work at the system call level, it doesn't really matter if your application, your code is running inside a container or not. We have full visibility across. And we have a CommonLine and courses interface. Internally, Sysdig, what it does is basically this. We have like an event stream where we put all the system calls, open, read, close, connect, whatever. And then we have these different actions, dump to disk, filter, or analyze. What we did, or how we built Sysdig tracers was, OK, so we have this event stream. What we can do is to insert markers here. And basically, a marker allows us to delimit what we call a span. A span can be everything. We can have function calls inside, network requests, any piece of code. You can use this from any language because basically how we mark spams or we do these marks is like writing into dev null, because at the beginning we thought about using a special /dev device. But when we wanted this to work into containers, we thought, like dev null is available everywhere, so let's use that because we see all the system calls. And it has very low overhead. So you have the same event, but we do this write into dev null, so we insert one entry, and we do another write to delimit the exit of the tracer. So inside, you can have system calls, code, everything. I'm going to show you. You can nest different spans, so you can delimit different pieces of code or calls that you want to measure. And you can write manually to dev null using this format, very simple format, plain text. You can use JSON as well, but it's like more complicated. And the fun thing of this, like, this is like super weird, Jorge. What the hell have you done here? Well, this allows to do tracing in bash scripts, for example. So this is a piece of bash script. We just need to do an echo into dev null to delimit the entry of the spam, and another echo to delimit the exit. So if you look at here, this symbol basically delimits if it's an entry or an exit. Fun things you can do with all this. Well, we can measure latencies in your code. You can save tracers and filter traces with Sysdig. You can analyze with Sysdig, which is the course's UI. You can see the system activity inside of a span. So in the previous example, I could see the system calls doing inside. I can do trace-aware log monitoring. So if I have some code that's doing login, but I want to see only the login inside the spam, I could do that. And we can export these metrics or tracers. They have a metric associated, the latency, for example, and we can export them into Stats and get some graphs. We're probably going to see that. So this is everything I had on the slides. It's like less than 10 minutes. So I'm going to spend the next 20 minutes or so. We'll leave some minutes for questions, digging and playing with this. So when you walk out from this talk, you are already familiar with the tool. Again, it's a bit dangerous from here onwards. So please excuse me if something fails. So the first thing I want to show you is this example I showed before. I have a script here, bash script, that it's basically pinging to Google, or loading Google. So I'm going to run this script, and then I'm going to send this to the back. And these are the things I want to show you. But let me open Sysdig. Sysdig is the courses interface. This is pretty much like HTOP, but on asteroids. Because if you click here and B, you have different views. Like we have Kubernetes, other orchestration systems, but that's something different. Today, I want to focus on tracers. So if we click here, we have an histogram of how these tracers that we are running in the bash script is performing. So if I stop this, you see this is going to stop. Or maybe I have something running. Let me double check. No. No, I didn't stop. Okay, no, it didn't stop. Okay, so I can basically measure the latency of loading the Google website. But imagine I want to compare this with something else. So I was looking for a fast loading site, and I found the router. So I'm going to run this in parallel, and I can see the difference. So depending, like you have here the latency from nanoseconds into seconds, I can see here the router is pretty fast, while Google website is a bit slower. I can, like, this is just a view of histogram, but if I go here to tracers list, I can see them with the latency, but I can also get some reporting. Okay, so I get average time, minimal time, maximal time. Very simple bash scripting. We thought that this is cool, and probably people want to do more complicated things with it. I said you can do echoes or write into dev null, but we also created a wrapper for Python. Some community members, they wrote wrappers for Node.js, for Go. And I'm going to show you a Python example. Hello world. So this is probably small, probably better. So you just import our wrapper, and we can use either with statements in Python. You can also use decorators. I'll show you later on, to basically tag the pieces of code you want to have in this spans. So in this case, what I'm going to do is to do inside this tracer that I call it hello world. I'm going to do hello world, but then outside I have this other hello world. So if I run this, okay, nothing special. But let me see the commands. I can use now the CommonLine interface to do the following. Yeah, so let me first explain the syntax a little bit. Here we call Sysdig, CommonLine interface, and we apply a filter. We want to get the events stream, and from the events stream, I want to look at the spans and tags, and I just want to show the ones that they are inside the hello world. And with all those events, I want to pipe them into a script that we call chisels. And this one, for chisels are written in Lua. It's very simple to write your own. And this one, basically what it does is to echo everything that's going into a file descriptor. So if I run this, I see that a Python process is writing in PTS this string. Okay, so this is very simple way of individually analyzing the system call. I can do other things. I'm going to show you another example of chisels. So if instead of doing a print, I do an HTTP request, and I use a different chisel. Yeah, there we go. This one, instead of going to put this at the top. Yeah, this one, instead of doing an echo of the file descriptors, what we do is we format HTTP requests. So what I get here is I get the response code, the latency, the size of the payload. You can write your own thing. Okay, so it's kind of neat to do all this tracing with very little effort and lightweight. But we can do like more complicated things, and I'm going to show you how to troubleshoot a kind of like dumb or stupid API. So for that, let me see, I didn't forget, no, there we go. So I created plenty of files in here. Server, there we go. This is a Python server that it has a bunch of different API endpoints. One returns a Fibonacci number, one downloads a file. It's not really important. But I want you to see, what I want you to see here is how we use the Python wrapper. So you can use a decorator, and decorators actually, we can capture the arguments. So I can see the entry and the exit of each function. Or we can use with statements, as we saw before. So I'm going to show you this piece of code, because probably we'll be looking at this later. I can individually tag the handler, and inside of the handler, I can do nesting and do the headers. And probably I know that's going to be very fast, because writing the headers is fast. But for example, I'm interested in this. I'm just writing a random file, and we can look at how this performs. So I have this server running in a Docker container. Docker file server, nothing special. And also I have a client that it does random requests to this API. So I'm going to run this. Oh, sorry. I want to run this foreground. So we see the connections running here. Now I can run Sysdig live. And I can see, for example, the containers. Yeah, I got Sysdig agent. I'll show you that later on, but I can see my 2 containers. Click here, and I can see the Python and the process, and here I can see the system calls and the echo descriptors. It's collecting a lot of data. Maybe it's a lot for my laptop. I'm going to stop this. But if we go into tracers, I can see all the tracers going on here, all the information. I can see the spectrogram I showed you before. And now this is like a lot of different things. I see some slow requests, some very fast, and probably like if we are a developer or we are some operation guy running someone else's code and I'm trying to figure out, I don't understand this code. What's making these API endpoints going slow here? Like from this into this is a big difference. So I can start using Sysdig CommonLine to apply different kind of filters and find out what's going slow. So I have dumped this previously into a file. So I didn't have to wait for some time. So basically, I dump everything into a file, demo scap, which is like a TCP dump file, but with all the system calls. So if I run this, no, I was too fast, sorry. I can start applying different filters. So one very interesting one is span duration. I want to see what takes more than half a second to run. So I run this, and bam, suddenly I get all the system calls. Or no, I don't have system call here. I have the entry and the exit of the different tracers, and I can see the tags. So this gives me an idea of what kind of things are going to slow. I see like Fibonacci a couple of times, but it's mostly the download handler. So probably there is some function over there going a bit slow. Let's keep digging and see what we can do more. So if it's the download handler, I saw that that piece of code was doing some writing. So I'm curious to see what kind of, let me explain this first, what kind of input-output activity are doing each of the spans. So I can use, again, a chisel, which is called fdbytes by. And I'm going to use that chisel, and I want this chisel to aggregate code based on the different tags. So if I run this, I get like a little report with the different tracers, names, or the tags, and the amount of I/O activity associated with them. So I can confirm that from all these, do, download, write, it has a very heavy input-output activity. But I'm wondering, what kind of input-output activity is this? Could be network, could be file system. Well, we have more filters. So let's see first network filtering. I just need to add another filter, very similar to CPDAM, that is file descriptor type IPv4. I run this, and I said, oh, half of it is network. Let me see how much is file system. I can do the same. So I see this guy is doing a lot of file system, and almost the same amount it goes into the network. So I want to see exactly what kind of files I am writing. So what I can do again is apply further filtering. So I can use this filter, fdbytes by, with a different parameter, the name of the file I'm using, and I want to filter out something. So I want only files, no network. I want only the system calls associated with the download handler and no others. And I want to exclude writing into the standard output because it's going to be dirt. So I see there are a bunch of different files, and one of them is quite big. So my assumption, what I can see, is that this piece of code is reading a big file and then is writing that into the network. That leads me to think that that's the reason why some calls to the API are slow. Where else I wanted to show you? This one. Oh. Last thing, I've been basically using chisels to aggregate and to format and report all the system calls. But if I'm interested in seeing exactly all the system calls happening inside of these spans, I just need to omit the chisel, use the same filter, and I get all the system calls. This is, if you see, we can go very, very low with all this tracing, but we can also do like a little bit higher end. So we have another chisel that takes all the tracers and we export them into stat.c. Stat.c, it's been automatically collected by the Sysdig agent we got here. So if I run this and I go here, this is Sysdig, it's going to take less or around 10 seconds. We'll see that the stat.c metrics will start appearing here. So let me load this. My server is not connected. No. Docker compose app Sysdig agent. I want to do this on the background. So this is sending, and I should see very soon my laptop in here. And the idea is that this is sending it into our product, but any stat.c collector that you got can be used to collect these metrics and do basically latency measuring. Something had to fail, or at least be slow. So second. There we go, delete it. This is my laptop. And we see that automatically we get here. I don't know if you can see this in the corner. All the different metrics. And in a few seconds, we should be able to see the metrics coming in. All right, questions in the meanwhile? Yep.
How do you instrument to get the system call and get the data? Do you use trace points or?
To get the data, it's, oh, here it's coming. As I said before, we tag an entry point in the event stream, and then we tag the exit point. And because we keep all this stream of system calls, we measure what's happening in between.
Yes, but do you instrument with trace point, or how do you get
What we have is, it's a kernel module that captures all this, and then it's our own technology, Sysdig, that measures what's happening inside. So we are not using anything like open tracing or things like that. I don't know if that answers your question, more or less.
I mean, do you know how it works in the kernel for trace points?
Yes.
Okay, so you're not using that.
We are not using that. We are considering moving into eBPF and things like that. Until now, on eBPF, we didn't have everything we needed to get all this information. So for example, I remember one of the limitations was that the buffer in eBPF only gave us like 4,000 bytes of every buffer of the system call. Correct me if I'm wrong, but now that has been extended. So there are a few things that it was preventing us to use eBPF. Probably this is that we change in the future, because the real magic, it's not like the kernel module, which is a very tiny thing. The real magic happens in the user space where you aggregate all the system calls. I think there was another question over there.
Yeah, what is the performance overhead for the containers that are being traced this way? Is there any, and if there is, what is the...
The performance overhead, it's very little at the kernel level, because all we do is in the case of tracers is to do an echo or a write into dev null, so 2 writes at the end, almost nothing. It can have more overhead when you move into the user space, depending basically on how complex are the filtering that you do and how big is your capture. These captures, they tend to grow very, very fast. So let me show you just, actually I'm going to do one. So this is just, so let's leave this like 1, 2, 3, 4, 5 seconds. This is 31 megs of 2 containers running HTTP requests as fast as they can. So if you run this on a production server, we have customers that just a couple of seconds, files, system calls, capture files can grow to 100 megs, even gigabytes. So if then you try to analyze one of those big files, it has an overhead, because this reporting, this aggregation of the system calls we do requires computing power. If you do that on a tiny file, it's fast. So depending on the amount of data you want to do the aggregation on. That one, and then.
Do you have support for following forks and things like that?
Yes, yes. You can filter your parent process. You can filter child processes. I think you can go your grandfather too. So I don't know how many nesting levels we support at the moment, but at least your father and your grandfather you can do. And that's basically the semicolon. There is one of one of the formats of this string you capture, you can follow your PID or your PPID. Actually, this is what we call that we have not only system calls, but we have events, because we don't, in this event stream, we just don't have the system calls, because that would be, I don't know, a trace, for example. We have some relationships between the system calls and some metadata information that allows us to do the different aggregation. That's the nice part of this.
Yeah. One question. I know this is a kernel model for capturing on all events, but if I want to trace, for example, a microservice that is multiple process in different hosts, there is kind of support to trace between different applications and more as aggregate or something like that?
At the moment, we don't have support for that. This is restricted to one single host. We are thinking how we should do this. Like, there are a few options. We can merge different capture files into a single file that then you can analyze. Our commercial tool, it does something similar. We don't have all the system calls. We have, we can get some metrics based on the system calls, and that allows, our commercial tool allows to monitor a distributed system and measure given metrics like service latency and things like that. But at the moment, there is no solution working out of the box for cross-host tracing. That's why this is like a pet project. It's something we just did in a couple of weeks, months, based on the previous technology. We are trying to figure out what we want to do with this. It's something, this is all fully open source, so maybe it's a project for someone to just say, hey, I want to merge Sysdig captures together into one file and then analyze them. It's a possibility. Yeah, no, go on. We have plenty of time.
Is there any support for tracing function calls on, in, let's say, Python interpreter, not just the system calls, but function calls in whatever language you use? Is there?
Yes, well, yes and no. We have some kind of support. So for example, probably the most higher level thing we can do is the tags. So, or the decorators, where we can capture the entry arguments and the exit arguments of a function. But we don't have like we don't have like a backtrace for a language or things like that. This is, we work in a lower level. It's very different. But I don't think there is an overlap. Like, we work at the lower level, other tracing tools, they work at a higher level, different use cases.
So how does this work with a language like Go, where you might have multiple Go routines on the same thread, interleaving their entries and exits and span?
We have thread support, but if I remember, there was some use cases that we were not covering. I don't have the full information. We have Go wrappers, so it's very simple to this, very similar to this Python. What was probably that we didn't have filtering support for threads? I don't know. I would have to check. You get a T-shirt. That's a question I didn't know how to answer. More questions? Feedback, comments? Yes?
The routing called environment, need I root permissions on the node?
Yes. So we require, or this requires root permissions, basically because we need to do an insmod to load the kernel module. If you, or during this demo, I've been running this on the host level. But for example, the Sysdig agent that was reporting the system calls into our commercial product, I was showing you here. This is running inside a container. So because all the capturing happens at the system level, and then we send all the system calls, or we collect all the system calls from the user space. It doesn't really matter if that user space process is either on the host or inside of a container. You can run Sysdig from a container, and you would have visibility outside of the container and into the host and across all the other containers running in the same host. If you see, like, this is the kind of metrics we get automatically here. No more questions? Well, if you have any other question, you will find me in our booth. You can come and say, hello, you like it, you didn't like it, whatever. Thanks very much for coming. I hope you enjoyed. And oh, some further reading. There we go. Thank you.